This is lecture 11, and we are going to look at a couple of very important modules, which is register file and memory. So we've been working with memory, but now we're going to take a more formal approach on this. Memory is very important because it stores data, and as you'll see, it also is intimately involved with I/O, which is input and output. Okay, so the register file is this item right here. We've used it extensively. It essentially interfaces with the memory, interfaces with ALU, etc., etc. So it's listed as a 32 by 32 memory. That's the capacity. So there's 32 registers, each of 32 bits. Now it's probably, don't need to get into it, it's probably actually more storage than that because it's a very highly specialized memory. And it's probably there's extra memory in there to make it do what we want to do. And so namely, it's specialized because it needs to support an instruction like this. So this instruction is just an add instruction. It takes the values in these two registers, adds them together, stores the result in that register. And the issue is that there are two registers it needs to read, and then it needs to write a third register. So it's simultaneously, or it has the ability to simultaneously read two different registers, or it could be the same register, doesn't matter, and then write a third register. So it's very specialized, and so people call this a multi-port RAM. Oftentimes we just break down and call it a dual-port RAM. Essentially means that it's not a simple RAM, in that our simple RAM has one address and then one output on it, one piece of data. So once again, it's reading two things and it's writing one thing, and so that's going to require that this object have three addresses. So here are the two read addresses, and this is the write address. I'm not overly excited about the names on these, but that's what we got for now. Right here is the data that's being written, and we also have enable, which is kind of a write enable, like we've been used to in other RAMs. The output has two 32-bit outputs, which is the output of the two registers that it can possibly read, depending on the instruction. Certainly not all instructions read two registers. Some instructions don't read any registers. And so, yeah, so the data on this is this input data here and output data. The address controls are, we'll say a clock and the enable, and then those are the controls, and then we have three addresses. These are the three addresses. Two of them are read addresses and one of them is a write address, and as you'll see in a second, these are actually going to be synchronous reads. Oh, there it is. Okay, so there's synchronous reads and they're there's asynchronous reads and they're synchronous writes. So this is the Verilog model for the reg file, and there's nothing really amazing about this. It's everything what we're used to. Certainly the first thing it does is model this is to write everything to a 0. So all the registers are written to 0. And essentially those registers are, you can see 32 registers, each of them 32 bits long. And 32 bits, that means we need addresses of 5 bits, and that's what we have here. This is the read data. So once again, once I get this right, the reads are asynchronous, and you can see this here. And essentially it's taking an address and using it as an index, getting the data at that address and assigning it to these two output values right here. So those are the reads, and like I said, they're asynchronous. You can tell they're asynchronous because the writes are synchronous. You can see that it's based on a clock edge. So the writes have a couple controls on them. Essentially, I have to turn the enable on, which is essentially a write enable, and I have to make sure that the write address is not 0. Now the issue is that x0 is always going to be 0, so I'm going to make sure to model this reg file such that the x0 register never gets written. So if it's the enable is turned on, I have a clock edge and the address is not 0. And essentially what I'm going to do is take that data and write it at the right address into the register object, which is essentially the array. We'll say that's modeling memory. So that's the register file. A fairly simple file, though it is a specialized memory in that it can read two things, and which are asynchronous, and it can write one thing. Here's the right address, here's the right data, and that is synchronous right there. So the working with memory, it gets pretty clunky. It gets really confusing because the main memory object, which is this thing I got right here, is very highly specialized. It's even more specialized than the register file. Now, so to keep track of this, there's actually inputs. They come in two different versions, and it comes in the 1 version and the 2 version. So a lot of these signals have a 1 associated with them. The other ones have a 2. Now, the issue is with the 1s they're associated with program memory. And so with program memory, certainly I can give it an input address, which is this one right here. It has a data output, and this is program memory. Both the program memory is synchronous, so I have to give it a read enable. So this is a control signal, this is data, and this is address, of course. Now, if you note, there's no write enable because this is program memory, and we don't have the ability to write it. So essentially, it's read only, which is not quite the case. If you know what you're doing, you can write over it. But generally speaking, you have no need to write over program memory. So I know there's an issue of self-commenting code or self-modifying code, but we don't do that. Okay, so that other memory is just the regular data memory, and that's everything associated with this to label. So the idea here is with memory, we're reading and writing memory. Okay, so the notion here is that the RISC-V, it does all memory accesses, whether reading or writing, through registers. So the idea here is if I'm writing a register, that's a store instruction, and I'm writing, so let's say that again. If I'm writing to memory, I use a store instruction, and it comes from a register into memory. So if I'm reading a register, that's a load instruction. It comes from memory and gets put into a register. So that never changes. And so the notion here is that all the transfers to and from memory are via registers. Really carved in stone, never changes. So for a memory access, we'll say, it must have a couple things here. Essentially, you have to give it an address, and you have to give it data. This happens to be a load word. So this is a load word. X3 is where it's going to put the data, and this right here is how it's going to calculate the address. Okay, so we've seen this before in that this is X8 is a base register, and this is an offset. Okay, so it's going to take what's in that base register, add the offset to it, and it's going to use that as an absolute address into data memory. So the data memory is also synchronous, so we have a read enable here. Also, data memory, I can write it, and so here's the memory, here's the data that's going to be written to it, and here is my write enable. And so that's it for writing, but it gets even uglier. So it turns out the memory module is extremely important for doing input and output. Now, in the big scheme of things, there's two types of I/O, we'll say I/O, input output, in microcontrollers. There's essentially they fall into the category of programmed I/O. Now, there's either an issue of port mapped I/O or memory mapped I/O. So port mapped I/O typically has its own dedicated instructions, like an in and out instruction. So the RISC-V does not have in and out instructions. It uses memory mapped I/O. So the inputs and outputs are identical to the load and store. Another way to say that is we use load and store instructions to do input and output. Okay, so load instruction is an input, and I'm going to take some input from the outside world and put it into a register. An output is we use a store instruction, which takes something from a register, throws it to the outside world. Now, so this is the issue here. It's still all register based. So for a load instruction for memory, I'm taking something from memory. This is a read instruction, not an I/O. Taking something from memory and putting it in a register. Okay, so if I'm doing an input instruction, I'm taking something from the outside world and putting it into a register. So for the store instruction is used to take something and put it in memory. So if it's a true memory access, it takes something from a register and puts it into memory. Otherwise, if it's an output instruction, it takes something from a register and sticks it into the outside world. So these are kind of confusing. If you keep this in mind, we'll be working with this. I think you'll get used to it. It actually, yeah, like I said, the more you do this, the better it will be. Okay, so the issue is that we're using the same instruction for both memory access and I/O. Okay, so something has to differentiate between whether that particular load or store instruction is an I/O instruction or a memory access instruction. So the notion here is that the hardware is going to differentiate whether we're doing input, output, or memory access instructions for us. So it's actually pretty it's a little bit different in real hardware, but we're modeling it at a high level using Verilog, so it's actually pretty straightforward. Yeah, like I said, it's more exciting in real hardware, but that's not where we're going to go there. So everything's based on the addresses, as you'll see, and essentially what it does is interpret the address and decide whether the hardware decides whether the programmer wanted to do input or output or memory access. So the memory space in the RISC-V is essentially 2 to the 32 times 32 bits. That's the memory space. And so what we're working with in the RISC is something limited, because we're going to implement this on the hardware, and our hardware is very limited. And so this is the address space we're working with. Now this is real memory. This is real physical memory. So we're limited to 2 to the 14th times 32, but typically speaking, this is a more useful number. We have 2 to the 16th times 8, and so this is our real memory range right there. Okay, so the issue is that we have 32 to 32 bit of address space and only this much real memory. It turns out I can use memory addresses above the real memory, and when I do that, the hardware interprets the particular instruction as an I/O instruction and not a memory access instruction. So once again, if my load store instruction uses an address in this range, then it is a memory access instruction. If the address is above FFFF, then that is an I/O instruction. The hardware is going to interpret that for us. Okay, so once again, in the end, it's the memory address that determines whether the particular load or store instruction is going to be a memory access instruction or a I/O instruction. So this is an example here of two instructions. They look exactly the same, but one's a memory access and one's an I/O. So essentially, this one is a memory access, because this address here is less than, the whole address here is less than FFFF. Okay, so this is an IO instruction because the address in X11 is greater than 0x0000FFFF. So the only thing that differentiates these is the address. If it's above FFFF, it is an IO instruction. If it's FFFF or below, it is a memory access instruction. I always try to envision this with hardware that I'm used to looking at, and it's actually kind of tricky here, particularly with the I/O and the memory mapped I/O. So this is an example of what's going on in the load, and so this is something that becomes more important later. This memory is very complex. It does a lot of amazing things, and probably too complex, but hopefully this will help you understand it. So when I'm reading, that means I'm either taking something at a particular address and data and putting it on the output, or it could be an I/O where I'm taking something from the outside world and putting it on the output of memory. So what's happening here when I'm doing an I/O, that means the address is above FFFF, and what's going to happen is it's going to feed this input down here, and it's going to stick it on that output up there. That's when the address is above FFFF. When the address is below FFFF or below, it's going to take this data and stick it on the output. So once again, this is coming from inside the memory, and it's going to go on the output when I'm doing a memory load or read. Otherwise, if I'm doing an input, it's going to take the input data and stick it on the output right here. Now, this is a really important point when you start implementing this later, so remember this moment. Additionally, there's another signal here. Now, this other signal here is essentially a specialized signal. So when I'm doing an input or an output, this is actually for a output signal, which is a store signal. When I'm storing something, I'm turning the write enable on, but if that address is above FFFF, it also turns this on. So when the address is above FFFF, this signal matches this signal. So this is going to be a pulse, and so this is going to be a pulse also. And so this is super important. When we start talking about the wrapper, we are going to get a pulse that we send upwards. You can see this is the pulse right here. When I'm doing a output still, this is going to send a pulse to the outside world, and we'll use that later. Okay, I'm going to call that done.